Today I would like to show some animated videos regarding this wave mechanics. Firstly, we will show that de Broglie wave equation and wave nature of particle.
Wave nature of electron. In 1924, Louis de Broglie proposed wave nature of electron. De Broglie's equation. Bohr treated electron as a particle. But according to de Broglie, every particle of matter in motion has wave character. So these are called matter waves. Wavelength of matter waves. Lambda is equal to h by mv. This is called de Broglie equation, where lambda, de Broglie's wavelength, h, Planck's constant, m, mass of particle, electron, v, velocity of moving particle, electron. Derivation of de Broglie's equation. According to Einstein's mass-energy relation, E is equal to mc square, equation 1, where m is equal to mass of particle, c is equal to velocity of radiation. According to the Planck's quantum theory, E is equal to h nu, equation 2, where h, Planck's constant, nu, frequency of radiation, equalize 1 and 2. mc square is equal to h nu. But nu is equal to c by lambda. mc square is equal to hc by lambda. Cancel c on both sides. mc is equal to h by lambda. Therefore, lambda is equal to h by mc, equation 3. This is de Broglie's equation. De Broglie relation. Definition. The momentum of a particle in motion is inversely proportional to the wavelength of the waves associated with it. From de Broglie's equation, lambda is equal to h by mc, equation 1. But momentum of photon, p, is equal to mc, 2. Substitute equation 2 in equation 1. Lambda is equal to h by mc is equal to h by p, where h is constant. Therefore, lambda is directly proportional to 1 by mc, or lambda is directly proportional to 1 by p. This is de Broglie's relation.
I never realized how important.
In this video, we have seen that de Broglie wave equation, and the next, the application of de Broglie wave equation. The de Broglie wave equation can be applied in the Bohr atomic model. So, as Bohr said, the quantization of orbits. So, here also, according to the de Broglie, the quantization orbits also is present. So, how the quantization of wave and how the quantization of orbit is related to each other, we will see in the next video.
Hi, this is Annika. Today we are going to take a look at de Broglie's atom and its significance for the quantum model of the atom. Louis de Broglie's model of electron behavior of 1924 was a critical step towards Schrödinger's quantum mechanical model of the atom of 1926. De Broglie developed a model that was able to explain the quantum behavior of the electron that Niels Bohr described in 1913 in a remarkable application of the light quanta of Planck and Einstein several years earlier. However, Bohr had no explanation for a quantized electron, which made many scientists skeptical. To understand de Broglie's model, we need to first understand Bohr's description of electron behavior, and then we can see how de Broglie was able to explain how a quantum electron could exist, which introduced the wave-particle duality of particles with mass, something we will go further into a bit later. In understanding understanding Bohr's model, we can better see why de Broglie's contribution was so crucial to the development of the quantum mechanical model of the atom. So first, the Bohr model. The most prominent feature was that electrons orbit the nucleus. But what was more important was that the orbit radius correlates to the electron energy. The larger the radius, the higher the electron energy. Let's take a closer look at the orbits. You can see that the orbits are at specific distances from the nucleus, and so the electrons have only the specific energy allowed by any particular orbit. Bohr stated that electrons transitioning from the higher to lower energies emit specific colors of light. We can see here that the larger the transition, the higher the photon energy, and the photon's energy is equal to the electron's change in energy. The electron transitions from a higher to a lower energy, and the difference is equal to the light energy emitted. This model of the atom came out of Bohr trying to figure out why various elements and compounds emit very specific frequencies of light, something that had puzzled scientists for decades. What is crucial here is Bohr's contention that the electron could only exist at discrete energies. In other words, the electron is quantized. If the electron could exist at any energy, then light could be generated at any energy due to the electron energy transitions occurring at any energy rather than discrete energies, which we would observe as an entire rainbow of colors emitted rather than discrete individual colors. We don't observe a rainbow. We do observe discrete colors, and so the electrons can only transition between specific orbits. And therefore, electrons can only exist at those energies. They cannot exist at energies in between. However, Bohr had no explanation for how the electron could exist like this, in what is called a quantized state. Where electron energy is discrete, Bohr's idea was a remarkable application of Planck's and Einstein's work, showing that light energy is quantized. But light has no mass. However, Bohr was quantizing a particle with mass, the electron. So now we can look at de Broglie's model as an explanation of Bohr's description of the electron as being quantized, electrons only existing at specific discrete energies. So Bohr's model of orbits was supplanted by de Broglie's model of the electron traveling as a wave. What is important to understand about this wave behavior is that the electron is in phase with itself. It meets its own path as it travels around the nucleus. This is called a standing wave. And the electron can only exist as a standing wave at specific discrete energies. This is a commonly known function of standing waves. Here we have a path with 4 waves. What would happen if the electron went to a higher energy level? Let's say from a path with 4 waves to a path with 5 waves. The standing wave with 5 waves would have to increase in size to accommodate the 5th wave, and so this higher energy path is larger. And so this higher energy electron is therefore further from the nucleus. This is what Bohr had stated with his circular orbit model, but without explanation. Here, the size of the path would have to increase exactly to the point where another wave could fit into it. And so the electron can only absorb the exact amount of energy that will allow it to move from one standing wave to another. Bohr's quantized electron now makes sense. Let's enlarge the new standing wave for the sake of clarity. So, if the electron has gained the exact energy needed to go from a standing wave of 4 waves to 5 waves, it will exist at a standing wave of 5 waves. This brings up the question, what if it absorbs some amount of energy that is not enough to get it to a standing wave? Let's see what would happen. The electron would not be in phase with itself. It would not exist as a standing wave. The electron would interfere with itself and could not exist on a path that was not in phase, a path that interferes with itself. This is a beautiful explanation of Bohr's quantized electron. A very important part of Bohr's model is that if the right amount of energy is absorbed by the electron, it can then go to a higher energy orbit. Here, the energy of red light is absorbed by the electron, which pushes it to a higher energy wave, but it will want to get rid of excess energy, and does so with the release of red light, while going back to a lower energy orbit. This explains the specific discrete colors coming out of energized elements. For de Broglie, if the right amount of energy is absorbed by the electron, it can then go to a higher energy standing wave. Here, the energy of red light is absorbed by the electron, which pushes it to a higher energy standing wave, but it will want to get rid of excess energy and does so with the release of red light while going back to a lower energy standing wave. The electron cannot absorb any other energy, for example yellow or blue, because those colors do not have the energy required to get the electron to another standing wave. This explains the discrete colors coming out of energized elements. Bohr was correct in his remarkable application of quantized light to a quantized electron, which was subsequently shown to be correct through de Broglie and the current quantum mechanical model, and many experiments confirming that electron energy is not continuous but discrete. The electron can only exist at allowed energies, and so we say the electron energy is quantized. So, de Broglie succeeded in describing a mechanism in Bohr's hypothesis of electrons only existing at allowed energies. This established the wave-particle duality of matter, a monumental step in our current view of the universe. It earned de Broglie the Nobel Prize in Physics in 1929, only 5 years after its publication as part of his PhD thesis, and was a critical step in establishing the quantum mechanical model of the atom 2 years later by Schrödinger and Heisenberg, a model which is intimately based on the wave properties of the electron devised by de Broglie. The electron's wave property presented in this video was de Broglie's interpretation of the mathematics he established to describe this wave-particle duality of the electron, but it is in fact very different from the now more established interpretation of the electron as wave. In 1926, Max Born interpreted the standing wave of the electron to represent the probability of where an electron is within the atom. One last fun bit about de Broglie. When he presented this work to his PhD committee, the mathematics establishing wave-particle duality, the committee could find no fault with the math, but they had great difficulty accepting an electron behaving as a wave. To help make their decision of whether to give de Broglie his PhD, they sent off de Broglie's dissertation to Einstein, who wrote back and told them that the idea had merit. So, de Broglie got his PhD in 1924, 1926 saw the establishment of quantum mechanics, and in 1929, the Nobel Committee also thought his idea had merit. Thank you very much.
I got this crazy idea. I thought,
We have seen that how stationary waves are present in the atom, how the stationary waves are related to the Bohr atomic model standing stationary orbits, and how the waves associated with the electron and those are in a stationary orbits. In the next video we will see an experiment, that is Davison-Germer experiment, which is the proof for electron waves, matter waves. Davison-Germer experiment is a proof for the matter waves, which is proposed by de Broglie.
Germer established the wave nature of electrons. Curiously similar setup to the experiment conducted by Davison and Germer. The setup is placed in an evacuated chamber. It consists of an electron gun G, a nickel target, and an electron detector that is capable of moving on a circular scale. The electron detector is connected to a sensitive galvanometer used to measure current. The electron gun G is used to produce a beam of electrons. The electron gun constitutes a tungsten filament, F, coated with barium oxide, and can be heated with a low voltage power supply. Electrons are emitted by the filament, and these are accelerated at a desired velocity by applying a suitable voltage from a high voltage power supply. The electrons thus emitted are passed through a cylinder with a pinhole along its axis, producing a fine collimated beam. This collimated beam is directed to fall on the surface of a nickel crystal. The electrons are scattered in various directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector or the movable collector. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering. Theta, which is the angle between the incident and the scattered electron beams. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity I of the scattered electrons at an accelerating voltage of 54 volt and at a scattering angle theta equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From electron diffraction measurements, the wavelength of matter waves was found to be 0.165 nanometers. We know that the de Broglie wavelength of an electron is denoted by lambda is equal to h by p, where h is Planck's constant and p is the momentum of the electron. If the electron is accelerated from rest through a potential difference of v volt, then, substituting the values of mass of the electron, charge on the electron, and Planck's constant, the expression for wavelength is obtained as 1.227 by square root of v nanometer. In this experiment for diffraction of electrons, the peak value of intensity was observed at 54 volt. On substituting this value in the equation and simplifying, we get the associated wavelength equal to 0.167 nanometer. This theoretical value is in agreement with the experimentally obtained value of de Broglie's wavelength for electrons. The Davison-Germer experiment thus confirms the wave nature of electrons and the validity of de Broglie relation. The de Broglie hypothesis has been the cornerstone of many advancements and applications in recent times.
Here we will see another explanation for the same Davison-Germer experiment.
Davison and Germer experiment. In 1924, Louis de Broglie postulated that all forms of matter have both wave and particle characteristics. According to this hypothesis, electron, just like light, have a dual particle wave nature. Two American physicists, C.J. Davison and L.H. Germer, were the first to experimentally prove the wave nature of material particles in 1927. Displayed here is a block diagram of the experimental setup used by Davison and Germer. It consisted of a nickel chloride crystal, the target, an electron gun, G, and a detector. The electron gun produced a beam of electrons. The electron gun used by them consisted of a tungsten filament, F, and high and low tension batteries. The low tension battery was used to heat the filament. A red hot filament produced an electron beam. A high tension battery was provided to accelerate the electron beam. The detector or the electron collector moved on a graduated circular scale. A sensitive galvanometer was also connected to the detector. How did they perform the experiment?
The electron beam was made to pass through a pinhole and made to strike the crystal normally. The electrons scattered in all directions, acting like waves. They observed that at certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves. Thus, they experimentally proved the wave nature of electrons. Davison and Germer plotted a graph taking the angle between the incident and scattered direction of the electron beam, phi, along the y-axis and the intensity of the scattered beam at different values of accelerated potentials along the x-axis. The nature of the graph is shown here. From the experimental curves obtained, the following conclusions were drawn. Intensity of scattering depends upon the angle of scattering, phi. A bump or kink always occurs in the curve when phi is equal to 50 degrees. This bump or kink increases as the accelerating potential difference is increased. At 54 volts, this bump is maximum and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons. Thus, Davison-Germer experiment verifies de Broglie's hypothesis of wave nature of matter particles.
Here you can see the double slit experiment for electron to prove the matter waves. So here one more interesting thing also you can observe in this. When the beam of electrons, the continuous flow of electrons will give the interference pattern when go through the double slits. Even after passing a one by one electron, even though you can observe the interference pattern. So that we will discuss after seeing this one, and I will show another experiment which is a question mark in the quantum mechanics of wave nature of particle.
Theory that we are living in a matrix-like simulation. You may know about or remember one of the most famous experiments in the history of physics, the experiment of Thomas Young, the double-slit experiment. It was a real coup in physics and led many scientists into the study of quantum mechanics. If you throw solid balls at a shield with a slit cut into it, a single diffuse strip designating the strike points will appear on the screen behind the shield. If there are two slits in the shield, then there will be two strips. But how will waves behave if aimed at the shield? They will pass through the slot and spread out. The greatest impact of the waves will be in the line of the slit, as in the case with the balls. But if you add a second slit, everything changes. A number of alternating interference strips will appear on the projection screen. And when we shine light on the two strips, this is exactly what happens. And this is how Mr. Young, the wave theory of light. If light were corpuscular, like a particle, instead of wave-like, it would behave like the balls, and the screen would show two strips of light corresponding to the two slits. That didn't happen. Later, it turned out that electrons and protons behave exactly the same way, showing that they also seem to exist as waves and not as points. There was one assumption that perhaps light and the others were particles, and that somehow the particles bumped into each other and flew apart. So, to test this, physicists decided to shoot electrons at the target one by one, single file. And what do you think happened? The strangest thing imaginable. The interference pattern still appeared on the screen. It seemed that the single electrons somehow divided into two waves, passed through both slits, then interfered with themselves. Impossible. So physicists tried to find out through which gap the electron actually passes. They installed measuring instruments to check this. Another seeming impossibility occurred. The electrons stopped behaving like waves and began acting like particles, and left a trace on the screen of two distinct strips with no interference. They had to admit something completely mind-blowing, that the fact of our observation or measurement destroyed the wave function of the photons, causing them to become like points, corpuscular. The electron, under the influence of observation, behaved like a particle flying through one slit and not through two. Interpretations. Well, it certainly looks like the work of a game engine, doesn't it? This might make you think that our world is running like a game on a computer. The computer's power is not enough to calculate the motion of each and every particle, so it uses a simplified model and applies precise calculations only if an observer needs to look at the particle, so as not to break the illusion of the reality